welcome to all of you. It's great to see you here, and I'm looking forward to an exciting couple of days. I've entitled the talk, Fixing Maths Education in the Era of Computers. And the sort of underlying theme here is the real world change, how should we react in education? No more central in maths, but applying to other subjects. And really what I want to take this talk doing was to point out that we are 5 years in since we formally started computer-based maths, although in fact a lot longer since we had the idea to do this. And I guess the thing I want to ask throughout this talk is, how are we doing? How's it going? And how do we take the next steps forward in moving it to a new phase? So really, I want to sort of focus my comments around 3 areas. Vision. How's the vision doing? And what are we doing in terms of the elements of change to make in order to promulgate that vision? Is that vision producing the appropriate elements of change? And then what is the progress we're making and we need to make into the future? So I'm going to whiz through the first thing about the vision, and I sort of apologize for this, but I'm going to do it anyway because I think it's important. I want to restate the vision. Most of you are familiar with the vision, but I want to make sure we're all on the same track quickly, because I think that way we can have a better discussion. So I'm going to kind of reiterate the vision for computer-based maths and hope that that will help us. And then I want to move on to how we're doing with that. So the central problem that we've identified is there's a real-world subject of maths and there's educational maths, and they are dramatically different. Why? Because of computers doing the calculating. And I, more or less say the good news is, if you're interested in maths, as I think everyone in this room is in some sense, the good news is that people around the world consider maths more crucial than they ever considered it before. In the real world, it's kind of maths, it's an era of maths compared to any previous era. Maybe the era will get bigger. The bad news is, if you're in maths education, it's maybe 80% different between education and the real world. And that 80% difference is largely to do with mechanized computation and the fact that that's allowed maths in the real world to be so successful. So we need computers for calculating, just like they do in the real world. And in order to understand this properly, we need to step back and ask, why are we learning maths? And in particular, why does everyone need to learn maths? And I think there are 3 good reasons for the right subject. Technical jobs that so drive our economies and individual success. What I would call everyday life. Even when we started the Mathematica project nearly 30 years ago, life was incredibly much less quantitative. Just to survive in a modern or even less modern society now, you need to be pretty quantitative. And thirdly, logical thinking. How do you think about life? And is there a dimension of thinking about life that maths can give you, whether explicitly or implicitly? And I believe there is. I think most of us here who are sort of mathematically trained in some sense have a way of thinking about things that people who aren't lack. That doesn't mean everything has to fit with that, but it means it's a very useful dimension. What is maths? What are you doing when you do maths? I think that there are sort of 4 steps. You are defining questions. If I talk for too long in this room and we seal it, how long can we all survive? Assuming various assumptions that there's no air conditioning blowing stuff in and out and so forth. It's always important to have assumptions. Can I translate that into an abstract form that I can then use to solve? Then step 3, the crucial step. Can I get the question of step 2 in its abstract form to the answer through this magical computation layer? This transformational process that's been worked out for millennia. And then the 4th step, can I take that abstract answer, x equals 3, and can I turn it back to actually answering the original question? So that's sort of the steps we need to go through in doing maths in the real world and in education. The problem we experience is we're spending almost all our time forcing the world's population to do step 3 by hand. And that has several effects, but one of them is it squashes the other steps. So 1, 2, and 4 are now much more minimized steps than they ever were. And that's sort of the crucial nub of what we need to deal with. How on earth do we change what's being done, for 106 lifetimes per year around the world every day into something that makes much more sense? So we need computers to do the calculating. We need humans for these other steps, much more, at least at the moment. That may change too, but right now that's where we are. And we need to remember that this is sort of a problem-solving process. What is the point of maths? You know, you can say the point of maths is because we're all excited by maths and maths is its own point. That doesn't get you very far logically, in my view, in explaining why the world's population should learn it. What's better is to say maths is a great problem-solving process. Maths is a fantastic way to solve problems. It's a process that's worked incredibly well. And, the process is we go through these 4 steps. We may iterate several times to go around until we finally get something that we consider is sort of an appropriate level of solution for the question we were asking. So maths is much bigger than calculating. And one example I like to give, and apologies if you've seen this before, here is a thing you would do normally in school, right? You would solve a simultaneous linear equation. What's a little shocking is that although the theory of solving that and the theory of, so to speak, what you're trying to do in solving a cubic equation here are the same, the output's different. But yet, if I ask most people at school, can you solve this? They'll say no. After 10 years of learning stuff at school, they can't solve it. In fact, it gets even worse than that. So let's see if this works. But Siri Willing, which I'll go back here, solve x cubed plus 2 equals 2y, and y minus x equals 5. So as I say, Siri Willing, we will see what we get. And that doesn't, oh yes, no, there we got it. Okay, so there, I've talked to my phone, and there in sort of 20 or 30 seconds is Wolfram Alpha has produced the answer through Siri, because we power Siri for these things, with all its, a graphical and Argand diagram and all sorts of stuff, okay? It's pretty shocking that around the world we are spending 10 years of everyone's life failing to get them to be able to solve what I can do on my phone by talking to it in 30 seconds. We got to seriously ask why the hell we're doing that, and we are, and that's what this conference is about. Okay, so what are some consequences of this? One of them is you can reorder for concepts not calculating. And one of the themes as we go to this conference is, what are the things we should be teaching earlier and later? See, it seems to me calculus should be taught to 10-year-olds. Why do we leave calculus so late? I think the reason is because integrals are hard to calculate. But actually the idea of, how much, to make these nicely shaped tables, how much material do I need? Or what's the gradient of a curve? What's the area under a curve? These do not seem like terribly difficult concepts, actually. Ones that are very amenable to most 10-year-olds. So if we, and again, the proof that, a derivative is the opposite of an integral, who cares at that stage? That's more complicated to understand that. Right? What's much more interesting is, here's a great thing that calculates areas, volumes. Here's a thing that calculates gradients. How can we use it? There are lots of fantastic ways to use that. Geometry. Should we be teaching 3D or 2D geometry first? Not obvious. To me, we all learn 2D geometry first, but it's actually, we function with 3D objects most of the time. So it's not at all clear to me that that's the right way around. Maybe it is, maybe it isn't, not sure. Image processing, crucial in the modern world, getting more crucial. Lots of things connected with that. What is the maths we really need to understand in order to operate that in a useful way? So these are just a few of the things that I think can be reordered and rethought, but that's some of the work we have to do. How do we reorder? How do we rethink this so that it's meaningful, but that it makes sense for the real world as well as education? Another thing we've got to remember to do, let's try and reclassify maths, not by what's inside, but by what it does. These are not terribly exciting topics for most, teenagers. Calculate long division, complete the square, the chain rule. Surds, my personal least favorite. Today's requirements for maths. What's the perfect password for my login so my friends don't break into it? Or GCHQ or whoever, if you're in the UK, the CIA. Are incentives working? How do I design controls for my game? How much do I compress a photo until it actually makes a difference and I can tell that it's compressed? These are the real, actual applications of maths that drive what we need. And we need to work back from those to figure out what it is people need to understand. What's a beautiful shape? Perfectly valid mathematical question. Not all of these have to be directly, sort of mechanically practical. They can be things that are aesthetic, but they need to tether to a problem where we can understand what the problem actually is trying to get at. Possibly the most crucial thing that I think people misunderstand, particularly governments, is if you remove the computer from maths education, you are going to remove most of the context. This is not that obvious. So here's the rationale. The reason maths is so important in today's world is because it works in many cases. The reason it works in many cases is because we have mechanized calculating. It did not work very well for many subjects, most subjects before that. It worked well for bits of physics. It worked fairly well for accountancy. It did a lousy job in biology, anything involving big data. Any of those things just totally not covered. Statistics is pretty much a field post-mechanized computing in practical ways. So therefore, if you take out, and so the reason governments and everyone are panicked about we don't have enough people coming out who know any maths is because maths is so important. It's so important because of mechanized computation. So if we go back into education and we say, okay, let's remove the computer and pretend that we're going to learn how to pretend to be a computer lots of times, we will remove most of that context necessarily because the context never existed. So we end up with toy problems that are too simple, biology problems that never got done with maths. Nobody will be interested in because they're too simplistic. So removing the computer does necessarily remove most of the context. If that's not understood, the maths that we're teaching will fail. Again, the more educational things I go to, the more I hear better deployment of the wrong subject, better teachers, better this, better that, okay? If it's the wrong base subject, it's not going to work in the end. And it's very important to sort of draw the line between these two. And in fact, one of the things I say, maybe I'm going to say it later, just to check I have. We talk about computer-based and computer-assisted maths. So you can have different words to describe these. What I mean by computer-based is the subject in the outside world changed because computers do the calculating. We need to reflect that in education, so it's the same subject. What I mean by computer-assisted is computers have a great role in improving pedagogy and improving the learning process, how students learn stuff. And I'm all for that. I mean, there are great things you can do with them, but it's different. That's what I call computer-assisted, and that applies to all subjects. And we need to be careful that the conversation about computer-based doesn't drift into computer-assisted. The two connect together because you need some computer-assisted to express computer-based. But computer-based is very specifically around maths and potentially computing and things, but is not, is less around history, for example. Talking of coding and maths, and again, this is all open to question this conference, I think of maths as a system of problem solving primarily. And in a sense, coding as a way to express and power it. And people who are specifically interested in coding have maybe a different definition, but from a maths point of view. But that means coding is very central, in my view. It is the way you write down the abstraction. You write down step 2 is with code. And that allows you then to compute it with a computer. So coding is very central, and we'll come back to that in a little while as to how I think that sort of connects. And I thought, just for some little light relief, I might just write a piece of code here. So what I was going to try and do, I thought it was sort of the stage in the talk where you might be a bit fed up with looking at me, so I was going to try and block out my face. And thought I would try and get our Wolfram language here to do that. So I'm going to try and show myself and a graphic of me, and I'm going to try and apply a rectangle to an image processing routine that finds faces. And let's see whether we can kind of make that work. And there we go. I am now officially blocked out. Not for very long, I'm afraid. But the point about this that's interesting is, what I've done here is I've taken some fairly advanced mathematics, and I've written a piece of code to sort of express what I'm trying to do in that mathematics in some sort of abstract way. So I've managed to plug in a sense, some quite nice algorithms. I've managed to write it down. I've got to order it. I've got to abstract it. And there it is, doing something, moderately sophisticated in one line of code. So I think it's quite exciting that modern technology allows one to do that. And we'll talk more later about technology. This is using the Wolfram language. One of the things I wanted to mention, and in a sense, the Wolfram language is one of the things it's trying to do is plug algorithms and maths into a high-level modern language. So you've kind of got algorithms included, if that makes sense. One thing I'd just point out, Scratch, which is a popular, particularly in primary, way of people learning coding, we are working hard on a Wolfram language Scratch sort of hookup so that you can transition from a sort of Scratch graphical look to a more language-based syntactic-based sort of setup as in Wolfram language. We'll talk more later about that. So, as I was saying earlier, computer-based, not computer-assisted, is the primary focus, but we do need to think about computer-assisted too. I want to move on to so that's sort of the vision, okay? What are the elements of making this change? What are the pieces you need to plug together to actually think of making this change? And then what have we actually done and how are we making progress? So, first thing I've been talking about, vision for the right subject and how it plugs into coding. Build the right subject. Not trivial. You know, what are the fields that we're talking about? What are the areas? How do they plug together? What's the order? What is it you really need to learn? What is it you leave to the computer? All topics for this conference. Align assessment. We might dislike that in many quarters, or we might like it, but the fact of the matter is, as the world currently is, people like to get numbers out at the end from assessments, and so aligning assessment is a very important piece of what we need to do in order to push this forward. We also need to fix maths marketing. I've said this before. You know, whether governments or whatever think that it will get them votes to say that we're going to pummel students through long division endlessly, it's not good marketing in the end. It's basically saying maths is a tedious subject that you shouldn't really want to do unless your parents kick you very hard. Right? This doesn't seem, whether it gets a few extra votes, it doesn't seem like it's a good long-term strategy in terms of improving people's interest in maths. We should cut it out and improve it. And I think there are lots of exciting things to say about maths. And indeed, one of the things in the UK, you know, a good example of this is a bloodhound race car, trying to make a car go 1,000 miles an hour. Can we, you know, that's an exciting use of maths. That's a good example, or some of the things, of course, we're trying to do here. We also need to be pragmatic and understand that there is a huge ecosystem that we need to mesh with. Again, we may not like all of it, but there's a certain amount of meshing. What I think is important is to keep the vision out there. One of the mistakes that's been made in previous maths reforms, or attempts at them, is that people are so concerned about what happens next term or next year that they totally lose any vision. Or maybe they didn't have the vision to start with, unclear. But whatever it is, they lose the vision. I'm pragmatic, but we've got to keep the vision out there where we're trying to go, even if we have to compromise en route. I want to spend most of the rest of this talking about progress and how we move that progress forward. So, vision. How are we doing on the vision? Well, this is an area where I'm incredibly happy. So, 5 years on, you know, I think people are coming round. It's not like I feel I'm fighting to get that somehow the vision has been sort of chiseled away at. I think the vision is stronger than ever, and in fact is proving sort of more robust even than I imagined it would be. People get it. In the end, if the world changed and we got computers and mechanics, mechanisms, you know, we mechanized the calculating. In the end, you know, we got to step up to the next level. Humans have got to get up to the next level and do something different. People get that. There isn't a fundamental problem, in my view, in most places with people getting that. And even if you look at organizations like PISA, for example, who, you know, the PISA tests driven by the OECD's committee on that. You know, I was recently at a conference, as was Jack actually, and others. You know, there's some understanding that the world's subjects have to change, and we've got to assess to figure with those changes. I think we haven't quite got the extent to which computers change maths and so forth, but there's understanding the subjects must change, and the computer-based maths sort of is a direction that sort of needs to be gone in, problem-solving maths. So I think, you know, Andreas Schleicher and others like that do understand that this is an important sort of change, perhaps not its extent. The other thing I think I've understood about the vision is, politically, this is an interesting one to sell. So computer-based maths as a political sale in most countries, I think is not at all impossible or even that difficult. It's sort of, there's a lip to go over. There's an energy barrier. It's not totally straightforward. But it's not something that's hard to, you know, in the end, if the idea is to tell parents, most of whom hated mathematics, that somehow your children can do something that's more valuable to them, they'll probably hate a lot less, they might even enjoy, and that fits with modern ideas of coding and of using machinery where you can. This is not a very difficult sell in most, you know, most countries. And I think that we need to push our politicians to make that pitch. It's not a trivial one-headline pitch, but it is one that I think will stand up very well. Surprises for vision. I am monumentally surprised as it remains. I thought when I started this that hostility would be the main problem. I think I'm wrong. I think it's confusion, total and unmitigated confusion at every level. Most people involved in maths, I think, don't understand why they're doing it. They don't understand what it's doing for them. They don't understand why they're teaching it, and so it goes on. Now, there's some fraction of those that are just, fundamentally disagree. You've got to learn how to do it by hand because that's what you've got to do, and I'm very happy to have the discussion with them. We tried to get some here today, actually, but some of the people from the UK weren't quite so keen to engage in that. So I think we just got to go on making the vision very definitively because I think people are still somewhat confused. They still say, oh, yes, it takes them a few rounds to get it. The other thing is applicability to other subjects. People don't get, or I didn't understand. I suppose the surprise for me is some of the things we're saying about computer-based maths actually apply to other subjects too. Like the real world changed and the subject didn't change too. It's just that it's less, there's some less, computers just fundamentally uprooted everything that was sort of, the sticking point for hundreds of years with using maths was that you couldn't do the calculating. And then computers blew it out of the water beyond any imagination previously. Right? That hasn't happened in another mainstream subject in the same way, and so therefore you haven't had that complete re-effect. But I think the same problems still occur. The subjects lag what's happened, what education is doing. Or rather, educational subject lags what's happening. So an important world change in the middle of this is, 5 years ago, coding as a school subject was not on the radar. And actually, from Estonia to the UK in particular, and we have people who've been involved with this, from Jakob Viksu to Simon Peyton-Jones and others, here today, and spreading out largely from there, coding has seen a resurgence, which I think is great, in our classrooms, and is starting to gather pace as a subject that's a serious mainstream subject. And that's very, very helpful to what I think we're trying to do, and in fact, arguably, we'll come on to later, maybe something that combines. What's my target with the vision? I think the target is that it's so incredibly obvious to everyone that basically it appears that it was just something that happened all the time, and it was just, it's just obvious. That's what it is. That maths is just this subject, or whatever you want to call it. That's where the vision needs to be. In the same way as we think the idea that you can calculate things today seems just incredibly obvious. Nobody really questions that things get calculated in the world. But a few hundred years ago, this wasn't obvious at all. Most people didn't realize you could logically work out answers in this way. That just seemed alien and weird. I think that's the sort of a measure of how we've done. What do we have to do on the vision? I think we've got to hammer it. Hammer, 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 hammer until people understand what the vision is, amazingly more than I would. We also have to manifest it. But we've got to do both of those. And that's also where all of you and others can help as well in clearly sort of explaining the difference between computer-based and computer-assisted. Progress, outcomes. So one of the problems on this journey was I thought it would be fairly easy to say, hey, there are some outcomes of maths that everyone agrees about. The problem is they just got confused about how to get there. Unfortunately, this hasn't proved to be the case. And so I think we have made some progress on this, and I think we are, many of you will have seen our sort of outcomes tree, which I think is an interesting go at what the outcomes of maths should be. This is a 10-dimensional list, which we'll look at later, I know, in the conference. But it's basically a list of what are the outcomes you want. What I hear in many jurisdictions around the world is, outcomes, well, we need critical thinking. Yes, obviously, it's hard to disagree with that. And then you go into the detail, and they say you need to know where to put ticks on bar charts. Okay, but it seems like there's a gap between those two levels. And we're kind of trying to fill that gap. So it's like there's a manifestation of the critical thinking, the confidence, the other things that actually fits with what we're doing. The other thing I think we are sort of unique in having done is put together the process with the outcomes. The four-step process I described is quite hard to marry with the outcomes because some of the outcomes are part of the process and some of them are the whole process. And we've kind of married those together reasonably well, I think, and I don't think anybody else has really attempted that, including PISA. Surprises. The scale chasm I mentioned and the sort of confusion between mechanics and concepts. What is the tool by which you do things, and what is the idea? What's the idea of an equation and when you use an equation versus solving the quadratic? This seems monumentally confused in virtually all the outcomes I've seen, and I think is actually a great source of confusion to students, frankly. Okay, they learn the quadratic equation, and it's kind of hard to separate why you'd want equations, when you'd solve an equation, whether it's quadratic or cubic or whatever, or differential, from the quadratic actual formula. What do we got to do? We got to map to all of maths. So we've got to take these outcomes, we've got to figure out what it means for all of maths, and we've got to marry with assessment. That's a sort of a crucial thing. We've got to say, well, if you assess in this way, this marries the outcomes that we've talked about to the assessment, and I think that's very much a to-do. How are we doing on development, process of development? Well, I think we're doing well. I think we've started to build interesting materials and manifestations of CBM, and we started to use those in classrooms and test them. One of the surprises to me about this is how uniquely positioned we, as in Wolfram, as the backbone thing, and computer-based maths, therefore, as a sort of a spin-off from that, are. It's funny, but it only dawned on me way after we started this that it's kind of like we interact with maths in virtually more ways than any other organization on the planet. We, for 30 years, try to get people to use mathematics more. We build software to do this. We hire mathematicians. We work with, all areas of maths, whether it's art or physics or finance or whatever. So we have a huge body of people who are using maths. And it's quite interesting to see. I mean, one of the other things I often quote is, I think it's that 97% of people who buy Mathematica claim they're not doing maths. They claim they're doing engineering or something else. So that's very important, because that means that, as a rough guide, the uses of mathematics around the world are 97% not by, quotes, mathematicians. So we've got to be very careful when we set our curricula to make sure that we reflect that. The other thing, a surprise, maybe it's not, shouldn't be a surprise. It is incredibly, gruelingly hard to figure out how to change, what to do in terms of which things people need to learn and how you present that. Gruelingly hard, even compared to why? Because everybody who's involved in this is traditionally trained, like me, for example. And what you've got to do is separate what you know and how you learnt it from what you actually need in this changed era and how that can get across. Some of the educational theories help a bit, but they're theories about trying to do something different, and so it's quite hard to try and see whether they actually work. So that's a gruelingly hard problem we've got. Sort of process to do and target. I think my main objective at this point is to scale with quality. I think we've laid some really good roots, so to speak, for building what we're trying to build, at least in one form. The trick is to scale it, be able to build across all sorts of things, but keep the quality. And that's not to say we've not got stuff to learn. We've got plenty of stuff to learn. But one of the questions that often comes up is, can the community really contribute to this? And I'd love that to happen, but we're just not quite ready. And I've said this for a little while. You've got to get the quality. You've got to get the thing understood and kind of collimated sufficiently that people can understand what to do to plug into it in a way that doesn't sort of mush it too far. And so that's a crucial thing as a sort of a tipping point at which you can see the quality allows you, the understanding of what you're doing allows you to scale. Materials. I mean, the actual materials in terms of progress that we built, we started with data science, what I would call data science, probably in statistics. We're working on geometry. You can argue about what the areas of maths are. And it's an interesting discussion. In a sense, you should say, well, it's maths. Here it is, the whole gob of it together. That's really what you want people to know what to do with. But on the other hand, it's quite useful to break it up into different pieces just so you can talk about it. And I know we've been talking about 5 of these pieces, roughly. Data science, geometry, modeling, information theory, not quite happy with the name, architecture of maths are the sort of areas we've been talking about. But I mean, that's all open to different ways to slice. I never end being surprised. I thought, well, data science, obvious lot will change in data science. What about other areas? It's just amazing. Geometry, you start doing geometry. That's just a huge gob of change. It's just, I'm amazed by how much, I thought at the beginning of this project, maybe when we do this, actually not that much will be that different. Maybe we're just talking about something that's sort of, really quite similar. It really isn't that way. I mean, literally every stone you turn over, there are big creepy crawlies underneath as to why it's done. You know, it's all on the basis of you calculate, you learn to calculate, it's the wrong order, wrong thing, wrong presentation, isn't matching the real world. This seems to be happening everywhere so far that we've attempted. And one of the things I think is interesting to do is to try and just sort of look at, in a sense, if you look at something like geometry, what are the unique selling points of using a computer-based maths approach rather than traditional maths? What changes? So this is just a quick list. This was around geometry. We were thinking about this recently. You know, abstraction to and from 3D, nonlinear mappings and projections. You know, similar triangles are an example of mappings. Why on earth are we stuck on similar triangles? Well, because it was too hard to do more complicated things, right? But actually, they're just, you know, they're fantastic nonlinear mappings. But what you really want people to understand is mappings and projections. You know, relationship between mappings and projections. I hadn't really understood this till we thought about it, actually. You know, 3D locus of points questions. That's what you actually do, you know, in real life, a lot of. Computation with calculus, problem-less, you know, led coordinate system choice. I mean, this is just nuts. You know, let's learn a coordinate system, and let's basically convert everything to Cartesian, because we could calculate. We know how to do a vector product in Cartesian, so let's do it that way. Right? This seems nuts in the modern world. Let's match the coordinate system to the problem at hand. You know, I want to draw that bottle. Right? It seems sort of dumb to use a Cartesian coordinate system for it. Why don't I use cylindrical coordinates? It looks more like that. Let's start with that. So all wrong way round in traditional, you know, iterative geometry you can do, of course. You know, terminology of shapes and objects. You know, we shouldn't be embarrassed about people learning terminology. It's useful. The fact that I can say cylindrical coordinates, and most of you know what that means, more or less, is useful. Nothing embarrassing about people learning vocab, but it doesn't have to be muddled up in the proof of what happens with cylindrical coordinates. Those are different things. So those are just some of the sort of changes. What do we have to do with materials? We've got the other areas I mentioned to build out. We've got to build out through all levels. You know, I think we need to, we've been working more from the sort of, you know, older pre-university age than we have younger ages, but I think this applies further down the spectrum, and I think the earlier we can switch into this, the better. And we've got to have different deployments. So what I mean by that is, yes, we've got deployments in classrooms. What about self-study? What about adult deployments? All sorts of different ways in which we promulgate this. One of the pieces of other progress we've done, which I sort of hoped we wouldn't have to do too much of, was the delivery platform. So one of the problems when you start to think about, okay, so here's the subject, here's the materials, here are the ideas, what do we actually do? You know, we need to get these in teachers and classrooms and everything else. What do we do? What is it we deliver? How do we communicate this? So we ended up building a whole delivery platform. And one of the, so just thinking about the delivery platform itself as an entity, forget the content for a moment, which is the crucial thing. It's sort of a unique thing of trying to mesh the student and the teacher thing together, something you can do electronically, make it interactive. And I won't, actually, maybe I can just flick to an early example of, this is sort of where we're at on this at the moment. There are, you know, this is sort of a module, so to speak. And, you know, I can just go to different sections of the module, and hopefully things will work here. There we go. And, you know, there are different pieces of it. Now, this is the teacher version of the module. So we've got teacher boxes explaining to the teacher what to do if they're lost. Interestingly, we found teachers have mostly reacted very well to this. I thought it was horrifying. Tell a teacher what to do in every few minutes of the class. Actually, they've reacted well, because what they say is, if we know what's going on, that's great. You've been explicit about it. I can follow it or not follow it as I choose. If they're lost, then they can refer to this. And so that's actually been more helpful than I thought. So the idea is to build these things. So we've built this whole platform where you can swap information across the classroom and so forth. So in a sense, that's a side effect to what we were really trying to do, but I think is interesting in its own right. Surprises. One of my problems in demoing computer-based maths to people who've never seen it, or explaining it to people, is you show them something like I've just shown you, but in more detail. And what they look at is what the delivery platform looks like. So the first thing they look at is, here's, you know, there are nice controls, and does it match up to some other nice fancy thing I've seen on the web? they don't see the fundamental content change. And it's a problem of demoing it, because you want to explain the fundamental content change, but until you've gone through it for several hours, it's not obvious what that is. So one of our problems is just how we explain that, rather than just have people look at the WYSI platform, which I think isn't the main point. And that sort of dominates the first impressions. What do I count as platform success with computer-based maths? I'll tell you what I count as real success. When there is no platform other than the tool. When people open up a blank screen and they have a problem to solve, and they use the tool to solve the problem. They're not going to some built-out thing in education. That's real success. So in a sense, what we're doing here in building out the framework and things is all trying to communicate that to a point where you get to the fact they don't need it. And that's sort of the ultimate thing. Now, one of the huge mistakes in educational technology, which actually came out also at this recent PISA conference, was most of the educational technology made specific for education is pretty bad. And it's actually very easy to see why that is, because you've got a relatively small funding for it, and you're trying to do something rather complicated, which is completely askew from what's happening in the real world. The thing you should be doing, on the other hand, tools in the real world today are quite good. They've got lots of funding. They're big things. They've been just like We Build Mathematica. We have millions of customers for this. It's got funding. We can build it out. And so as much as possible, we should use real tools. Give the students the real tool. And the other exciting thing about this is we are in a unique era for this. In past eras, it was very hard to take the real tool and move it. It's hard to take a combine harvester and put it in the classroom. My computer is not much more advanced than the average computers in a classroom. You could just take the real tool. There's no excuse. There may be some things you have to build around it like we've done, but that should be what you're trying to avoid, not what the sort of main point is. So what do we have to do to the platform? We have to cloudify it. I think we have technology now to move what we've done locally into the cloud. I think that'll change deployments and make it easier. We have to improve many of the elements in those deployments as well. Assessment. I mentioned that earlier as a key point. One of the things that's exciting to announce here is that we have started a research project with Cambridge Maths, who are linked to Cambridge Assessment, a major assessment group in the UK and beyond, and worldwide, actually. One of the oldest assessment groups in the world. They have lots of experience. This project is to work on interactive materials and to make that progress, and also to see how that might link with assessment. So I think that's a very exciting new push and a way to combine skills there from different groups into a project that will hopefully move this along. So that's a sort of a thing that just recently we started work on. Early insights into assessment. I mean, one of the problems with assessment is many people believe assessments in general are completely broken. And I'm not totally disagreeing with that in some sense. But it's sort of hard to change all dimensions at once. And one question is, if you take a computer-based maths type of content, can you somehow plug that into today's assessment setups in a reasonable way? We don't know, but I think it's more hopeful than I would have thought a year ago. And we need to work on that. Of course, you need a computer in the assessments. That is kind of a foregone thing. But can you use traditionally a 2-3 hour exam with that to make it work? And I think we have good belief that that is possible and can be done. And indeed, we have David Lancaster here who's tried some such things with some of the maths in Australia and others, and we'll hear from David later. Some of the issues around this, though, with assessment are affecting all subjects, not just maths. What's the target for assessment? That we can deliver for high stakes and high volume. That people, that this is the mainstream thing that we can deliver for. And what's there to do? Pretty much everything. We haven't really got going on this properly, and that's something that we want to and need to. I want to spend a couple of minutes on evidence and innovation. So one of the things that's become clearer and clearer to me is how screwed up the ecosystem for education is in terms of innovation. And one of the sort of ways to crystallize this, I wrote a blog about this recently, is what you might call evidence-led innovation versus innovation-led evidence. So one of the problems in education is that people say you need evidence before you change anything. The problem with that approach is, here's the evidence, we've done lots of research, and here's what you do. The problem is you can make sort of micro steps of innovation, but you can't change anything much because there isn't the evidence to do it. Right? So this kind of means you can't make a change. what you need, I'm not saying you don't need evidence for things. You absolutely do, but you need the other way around. You need to guess. Make a highly educated guess with as much basic idea as you can. This is how science progresses too, how Faraday and others made progression here. They guessed. They then build out the consequences of a good educated guess. They then test it. That's what happens in drugs. That's what happens how we make progress in medicine. Right? If you muddle these up, there will be no innovation, and that is happening today in education. One of the problems with education is, the ecosystem. In many other areas of life, the ecosystem has moved forward quite well so that you can make innovations. That hasn't happened in education, and until it does, we are going to be horribly stuck. It's almost like saying, in order to build, we can't. There's a horse and cart, and we figured out how the suspension system for a horse and cart works. And somehow, when we build a car, we're going to have to assume the same thing. We can't make a leap there at all, even though you're doing very different things. So it's very important to understand the difference between those two. We like to have a theme for the summit. This year's summit, the idea was to address the question of how CBM will be practically embedded into the maths ecosystem all the way through, from primary to secondary and into adult. And it's good to just keep that in mind as we're going through. I wanted to sort of start to close by bringing up a quote that Jobs gave us in 1988, which I think is rather interesting. And the quote was, "Mathematical will revolutionize the teaching and learning of math," he's American, "by focusing on the prose of mathematics without getting lost in the grammar." Fantastic Jobsian sort of quote. There's one problem with this. So he was very right and he was very wrong so far. Right? And I've highlighted the pivotal word. So he assumed that Mathematica, at the time was what he was talking about, but you could talk about general computational technology, would revolutionize it. Well, it hasn't. And we're 25 plus years on. We're more than a quarter of a century. It hasn't happened. It happened in the real world, didn't happen in education. So will sort of is should. And I guess when I look back at this, which we only found again recently, fairly recently, it sort of emphasizes the lag that's there. And, but it also emphasizes how, I mean, it's a lovely way to express what I think CBM is trying to do, in a sense, which is don't get lost in the mechanics. Focus on the concepts that you can do now you have computerization. Where's maths going to be in 20 years? That's what we need to keep our vision sight on. I've said for a long time, I think this project, to get really, to the point where it's just obvious, is a 25-year thing. So we're kind of 20% in, would be my calculation, my basic level of calculating. It's interesting to compare with other things that sort of changed. And universal education was an interesting thing that pushed countries that did it earlier furthest. I think people who get CBM and can understand how that affects STEM and beyond will see a major push forward. And the countries and places that do this first will get the biggest sort of boost. That's not to say everywhere it's not useful to them. In terms of process, it's quite interesting to think about classics. I know the UK case better than other countries. But, one thing that happened when there was sort of, at least for grammar schools and things, universal classics, was that the classicists just assumed the subject would just never stop being universal. It was just obvious. They didn't need to justify it. There it was. You learnt Latin because that was sort of predicated as an important thing for any educated person. I watch a bunch of mathematicians now, and it feels very similar, right? It feels like exactly that. We're not going to justify why maths is important. It just is. And if that happens, maths will lose. Sooner or later, it will just dissolve into a side subject, like Latin and classics has. Whether or not you agree with classics being for everyone or Latin being for everyone, there are arguments for and against. They didn't make a good case for it because they assumed it was just there. And I think the same will happen with maths. So if we don't change to computer-based maths, I think that's sort of the process by which things will go. Sort of top 5 maths fixes and summit outcomes that I'd like to keep in mind. We need to get and define the right subject. We need to use computers for calculating. We need to combine with coding. We need to lead with the problem. Maths is the solution. And we need to make assessments match. I think if we can keep those sort of 5 in mind, that will help us a lot. So look, it's great to see you all here. I hope we can all together sort of unscramble maths into a modern computer-based subject. Thanks very much.